For those of you that understand better by hearing things, I'm going to make a video here of filling in the note, even though there's also a handwritten version available for you. So if you prefer to just go with the handwritten version and read through it yourself and you understand, fine. But otherwise, watch this video to get a little bit more of an explanation as I fill in the note. So exponential equations, recall, have to have an exponent of x. So we have something that looks like this: y equals a b to the power of x, where a is a number and b is a number, and the values for y and x are going to change as you graph them. A is going to represent your initial amount. So if we're talking about an investment, just say it's how much money you put in the bank, and then it's going to collect interest and grow over time. So B is going to represent your growth rate. But for other kinds of applications, it can also refer to the rate of decay, things getting smaller over time. For example, half-life, or the amount of caffeine that stays in your bloodstream over time, because your kidney and your liver are going to work on breaking it down and getting out of your body. We'll know, looking at that equation, you'll know if it's growth or decay based on what number b is, what number is in the place of b, which number, what the number is that has the exponent x on it. So you're going to have growth when b is greater than 1. So the first line here is when b is between 0 and 1, in other words, 0.6 or 0.5, anything less than 1. It could be 0.99. Either way, if you have 0 point something, you're going to have decay. Okay, the y value is going to decrease over time as x gets bigger and bigger. If b is greater than 1, then our y value is going to get larger over time, so we're going to call that growth. So for instance, if the number for b was the number 2, then that would represent doubling over time. Okay, the population of bacteria, just say, will have a formula of y equals, let's say you start with 1 bacterium, it'd be y equals 1 times 2 to the power of x. If I add a b value of 4, then that means it would multiply or quadruple by 4 each time, whatever the previous value was. If b is 1, though, you're going to have no change. And we can see that by looking at this for a second. If we have y equals, let's just say we start with 2 of anything, but you have 1 to the power of x over here. 1 to the power of anything is still going to give you 1. So as x gets bigger, you're still going to have y equals 2. It doesn't matter how you change the x value. So for instance, y equals 2, 1 to the power of 1 is going to equal 2. If I have y equals 2 and x equals 2, I'm still going to have 2 times 1. I'm still going to have 2, etc., etc. So some examples of where you would see exponential functions in real life. A really common one is compound interest. And we're actually going to work with this formula when we do the personal finance unit. The formula is A, the amount of money you have. A equals P. P stands for principal. It's the amount of money you start with or you invest, or maybe the amount of money owing on a credit card. The number 1 plus I represents your interest rate, to the power of n, which is the number of times the interest is going to be added on to your investment or to your loan. So we'll deal with that formula more later. Half-life, you're going to have a formula of y equals a, whatever that starting amount of something is. You have to have 0.5 for the b value if it's half-life, because it's going to cut in half. 0.5 represents 50% or half. And we have this interesting little exponent here of t divided by h. T represents the amount of time that passes by, and h is the half-life of the material. In other words, it halves every how often. So I have an example here to show how to use the half-life formula. If you're drinking a cup of coffee, you're going to start with 200 milligrams of caffeine in your bloodstream, in your body. The half-life of caffeine is 5 hours, so H equals 5 hours. How long will it take for you to have 10 milligrams of caffeine in your body? So our initial starting value is A. Our initial starting value is 200 milligrams. And what I want to know, when will I have a final value, a Y value, of 10 milligrams? How long will it take? Time equals question mark. T equals question mark. So I'm going to fill that into the formula. Using the formula I have up here, you're going to get Y equals 200, the starting amount, 0.5 for half-life, and half-life happens every T divided by H. Our half-life is every 5 hours, so T divided by 5. And I want to know when, what T would be when Y is 10. So I'm going to sub that into my equation. 10 equals 200, 0.5 to the power of T over 5. But look at that. We've got an exponent of T that we want to solve for, but it says a fraction. It's in a complicated equation. So our best option here, we don't want to do common bases. Can't find one. It's too complicated. We don't want to use systematic trial. Will take way too long. So instead, what we're going to do is we're going to solve this by graphing. So we're going to take the 10, we're going to graph it as y equals 10, and we're going to take the second half and we're going to graph it as y equals 200, 0.5 to the power of t over 5. Okay, so I'll go into Desmos graphing calculator. Do that now. Desmos graphing calculator. Let's open that up. And the link for this is on D2L as well, of course. So our first equation we said was 10, y equals 10. And our second equation is y equals 200 milligrams, because that's what you start with, 0.5, because that's half, and it's going to half every, my exponent is t divided by 5. So I'm going to graph that. I don't see anything on my screen yet, so I'm going to try zooming out, because I know I typed in my equations properly. I'm going to zoom out. Oh, there's the lines. And my point of intersection is at 21.6 and 10. So again, the first value in the coordinates is your x value, or in this case, our value of t, and 10 is the y value. So I'm going to go back to my page, this one. So we had point of intersection at t equals 21.6. And because our units for time are hours, as described in the question, that means it's 21.6 hours for there to only be 20 milligrams of caffeine left. So I've paused the video and I moved down a bit so that we can get to the third example and have some more room on the screen. A third practical example of exponential equations is the growth of bacteria, which I just mentioned earlier. So it's going to have the equation of y equals a starting amount of bacteria. Bacteria always double. If you're a biology student or if you've taken a little bit of biology, you would know that bacteria split in half to make new bacteria, and therefore they're going to double each time. 1 turns into 2, 2 turns into 4, etc. And we're still going to have an exponent of x. So here's a practical example to solve. Bacteria reproduce by splitting in half, therefore doubling their population size. So anytime you hear the word doubling, that means that your B value is going to be 2, whether it's bacteria or anything else. Maybe it's an investment. If your investment doubles, your B value needs to be 2. Given the right conditions, bacteria can reproduce every 10 minutes. If the original population size was 5 bacteria, so initial is always going to be your A value, how many bacteria, y equals question mark, how many bacteria would there be in 1 hour? Now, since they reproduce every 10 minutes, we need to use the 60-minute value. You have to use the same units in your equation. So we've got y equals, our A value is 5. You start with 5 bacteria. It doubles, so we need a 2, to the exponent of x. And the question is, what is y after 60 minutes? 60 minutes is your time. So in this case, x. So y equals 5, 2 to the power of 60. We've got all our numbers here. We're not solving for a variable exponent x now, so we can actually just solve this. We don't even have to solve by graphing. We can just do this right on our calculator following the rules of BEDMAS. So 2 to the power of 60, I'm going to use my calculator. 2 to the power of 60 is a, whoa, really big number. So I'm just going to leave that on my calculator, and then I'm going to multiply by 5. And you should get 5 point, this is how it shows on my scientific calculator anyway, 5.7646, etc. Because I'm rounding, I'm going to put a dot on my equal sign, times 10 to the power of 18. It's a huge number. This is the same thing as moving the decimal over 18 times. So this is really 5.7646, and there's more numbers, but 1, 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 bacteria. There will be this many bacteria after only 1 hour if you started with 5 bacteria. Isn't that crazy? So it's great to know these things. First of all, for knowing the importance of sanitizing or cleaning things in your house or even on yourself. But also we can check investment stuff. We can monitor populations. So that brings us to example 4. Okay, example 4 has to do with population growth, not of bacteria this time, but of people. So I'm going to pause the video and just scroll down for a second. Okay, so for demographics, the population of Ontario in 1985 was approximately 9.3 million. It's been growing annually at a rate of 1.5%. So if you have a growth rate of 1.5%, we can put that into our equation. So part A says write an exponential equation to show or model this population growth, where y is the population size. We have a starting amount of 9.3 million, which I'm going to simplify by just writing 9.3 instead of 9.3, sorry, instead of 9, oh, you know what I mean, lots of zeros. We're just going to avoid that. So we got 9.3 as our starting population. Our growth rate, to turn that into a B value, what we're going to do is anytime you have a percent increase or decrease, if you, when you have a percent increase or percent decrease, you need to turn the percent to a decimal first. So in this case, we've got 1.5%. When you take a percentage and you divide it by 100, it puts it in decimal format. So this becomes 0.015. Okay, and then you're going to add 1 to it because we have growth. If we had decay, then we would just leave it as 0.015, or we would subtract it from 1, sorry. If it's going to decrease by 1.5%, we would do 1 minus that amount. But if we have growth, so we're going to add it to 1, and so we're going to get 1.015. That's our B value. So we're going to put that in here. 1.015. Okay, it's greater than 1. That means we have growth. to the power of our exponent x. Part B says in which year, so x is years, right? In which year will or did Ontario's population first exceed 10 million? So first exceed. Whew, okay, so we want to know when y equals 10, because remember that just like we wrote 9.3 instead of 9.3 million, 10 will also be representing 10 million. So we want to know when y equals 10, x equals what? So using our equation, okay, using our equation, we're going to have 10 equals 9.3, 1.015 to the power of x. It's too complicated to find a common base, too complicated and time-consuming to do systematic trial, so we're going to solve it by graphing. So that means this part we're going to rewrite as y equals 10, and the right side of the equation we're going to rewrite as y equals 9.3, 1.015 to the power of x. When we go and we graph that using Desmos graphing calculator, y equals 10, and y equals, starting population was 9.3 million. We've got 1.015 to the power of x. There's our point of intersection. It occurs at 4.874. So point of intersection at x equals approximately 4.87. I'll round to 2 decimal places. And that's years. So at 4.87 years, we're going to first exceed 10 million. I don't want to round it to 5 years, because if I say that, it's actually going to be more than 10 million. I want to know, when does it first go higher than 10 million? Well, that's at 4.9 years, or approximately 4.87 years.